So what we're going to have a look here today is an algorithm that's known as the Hungarian algorithm, which is an allocation algorithm for these types of assignment problems that I have in front of me. So what I've got here is a series of 4 swimmers where they are part of a relay team and each swimmer has to swim a different stroke of the relay. And what we want to do is we want to allocate the strokes to each of our swimmers in that it achieves the fastest overall time for our relay team. And you can see with this allocation sort of thing that swimmer B has its fastest time in freestyle, but so does swimmer C and so does swimmer D. So we can't just give the fastest overall time to each swimmer here. We have to look at it and think about what allocation would give our fastest overall time. And because this is quite a small problem at the moment, we don't have many jobs, we don't have any different swimmers that we're picking from. So we could actually look at this for a little while and probably think to ourselves, where is the fastest allocation? And identify that just by looking at it. And if you spend some time, you'll probably end up realizing that this here would be the best allocation for the swimmers. All right. And it would give us an overall time of about 216. I'm assuming this is seconds here. So it would give us a fastest overall time of about 216 seconds. Now, the thing about this is we want to think about a process that we could do that guarantees us that that is definitely the fastest allocation for a much more complex network than this, or not network, assignment problem than this. In that we could have thousands of jobs, thousands of different people. How can we allocate this when we've got a problem like that? And that's what the Hungarian algorithm comes into. Now, the Hungarian algorithm is as follows, and I'm going to step through this in an example to explain each step. But what's important to note with the Hungarian algorithm is it is a minimizing algorithm. So the problem that we've got with our swimmers is we are trying to minimize the total time that we're going to compete with. So that way we're getting the fastest overall time. Now, we can use the Hungarian algorithm in maximizing problems, and I'll talk about what we need to do a little bit differently first with those problems towards the end of this video. But I'm not going to read through this. You can pause the video and have a look at this in your own time. But what I am going to do is step through the actual Hungarian algorithm. So looking back at our swimmers allocation problem here, the first step of the Hungarian algorithm asks us to have a look at each row of the algorithm. And in this case, we're looking at which swimmer is doing which stroke and what their times are for it. And what the Hungarian algorithm says is if we look at swimmer A itself, no matter what, swimmer A is going to take 52 seconds as a minimum across any of the 4 strokes. So what we do with this is we say, no matter what, they are going to cost us 52 seconds. And we subtract 52 from the entire row. So we say with the backstroke, it's going to cost us an additional 4 seconds if we allocate swimmer A to the backstroke. It's going to cost us an additional 7 seconds for the breaststroke. It's going to cost us 0 seconds extra if we allocate them the butterfly. And it's going to cost us 1 second extra if we allocate them to the freestyle. And we do that, we repeat that process for each swimmer. So swimmer B here, you can see that no matter what, they are going to take 49 seconds. And that's in the freestyle. So with the freestyle, there won't cost us any additional seconds if we allocate the freestyle to them. However, it will cost an additional 10 seconds on the butterfly. It'll cost an additional 18 seconds on the breaststroke. And it'll cost an extra 13 seconds for that particular swimmer on the backstroke. And we repeat this for the other 2 lines. So it'll be 51 for the next line, so there'll be 0 here, 7 for the butterfly, 13 for the breaststroke, and the backstroke is 4. And then finally for swimmer D, it'll cost us 48 seconds no matter what. And there will be 0 here for the freestyle, and the initial 6 for the butterfly, an additional 12, and an additional 10. And that now gives us a new array. These things are called arrays. It gives us a new array where we're trying to allocate them with the smallest number of zeros. However, we can actually do this both ways, and this is what step 2 now looks at, is let's look at the rows, the columns, in that we're looking at the backstroke, breaststroke, butterfly, and freestyle, and go, what is the minimum amount of time from here, the additional amount of time that we're going to cost no matter what. So in this first one just here, you can see with the backstroke, we're going to cost an additional 4 seconds no matter what, doesn't matter who we allocate. So it's going to cost an extra 4. And in the second column here, it's going to cost an extra 7. So we're going to subtract 4 from the first column, 7 from the second column, and zeros from the other 2 columns here. So our array then changes to look a little bit like this. So it'll be 0, 9, 0, 6. This one will be 0, 11, 6, and 5. And then these columns will remain the same. So 7, 6, and then 1, 0, 0, 0. And from here, what we're trying to do, and this is step 3. Step 3 tells us that we need to try and allocate draw vertical and horizontal lines to cover up all the zeros. But specifically, not just any number of vertical and horizontal lines, because we could just go 4 horizontal lines and cover everything up. We want the minimum number that it would take to cover all the zeros, the minimum number of vertical and horizontal lines. So if I looked at it, I could do a horizontal line here, I could do a vertical line here, and I could do either a vertical or a horizontal line just here. It doesn't matter which will you do, you will still complete the Hungarian algorithm fine. Now, what we do here, this is a test. We call this a vertical line test. We're checking to see, can we cover up all the zeros with only using vertical and horizontal lines in less than the number of the square array. So the number of rows of the square array. So if we look at the number of rows that we've got here, we've got 4 rows to our square array. So can we cover it up in less than 4 rows? And in this case, we can. And if we can cover it up with 4 rows, we're not ready to allocate using only zeros at this point. So what we have to do is we actually have to go to step 4 or 5, I think of this, step 4. We have to go to step 4 here, where we look at the smallest uncovered number. So if we look at our numbers just in here, we're looking at these 3 and these 3. Which one is the smallest of them? Well, it's this 5 here. And what we're going to do is we're going to subtract that number. So we're going to subtract 5 from all the uncovered numbers, like this. And we're going to add 5 to anywhere where we've got a crossover in our lines. So these 2 cross here and here. So we're going to add 5 to here, and we're going to add 5 to here. And we create a new array. So this will be 0, 0, 0, 6. This will be 4, 6, 5, 0. So it'll be 0, 6, 7, and 5. And this will be 1, 0, 1, and 0. And what we do is we now go back to step 3, where we're trying to cover this up again with the minimum number of lines, vertical and horizontal lines. So if we look at it here, we could cover this all up in here like so. I can see a duplicate here as well, so let's cover here. But you can see that no matter what we're actually trying here, it's going to take 4 lines no matter what to get all the zeros. So what that tells us, because the minimum number of lines it takes is the same as the square of the array, we're ready for allocation. Okay, and this is where I probably shouldn't have just used highlighter over everything. I'm going to have to erase it all. But we're ready to allocate our jobs, and we're ready to allocate them only using zeros. Now, if I could cover it up in less, what it would mean is we aren't ready for allocation yet, and I'd have to repeat what I just did in the previous step. So let me just fix this up very quickly. So 0, 6, 7, 5, and 1, 0, 1, and 0. So we now go on to our allocation step. Now, how do we actually go about allocating? We know we're ready to allocate. How do we actually go about allocating? Well, what we do is we look at our array, and what I start with is rows. So I'm looking for any row that has only 1 0. So row 2 here, you can see it's got 4, 6, 5, 0. It's only got 1 0. So swimmer B, we are going to be best allocating the freestyle to swimmer B. And you can see with swimmer C, backstroke is going to give us our lowest allocation with a 0. All right. Now we look at, because swimmer B is doing the freestyle, we can't allocate the freestyle to swimmer D anymore. So that leaves this job here, which is our breaststroke for swimmer D. And then it gives us swimmer B the butterfly. And we can then look back at our original times, and you can see our allocations match up with what we seen at the start. And our minimum swimming time is once again going to be 216 seconds. But we've found this allocation only using the zeros of a Hungarian algorithm. And that is the process of using the Hungarian algorithm. Now, there's some additional things that we need to be aware of as we're working through with the Hungarian algorithm. So let's talk about the little things that we need to be aware of as we start working. The first thing is, and I sort of touched upon this a little bit earlier, we need to have a square array whenever we're applying the Hungarian algorithm. If we don't have a square array, it means that the Hungarian algorithm isn't going to work. So you can see here that I've now got an additional swimmer that I can allocate to one of these 4 jobs, one of these 4 strokes. The thing is, when I've got an additional swimmer like this, what it simply means is one of these swimmers is going to miss out. They're not going to be required to swim a leg to achieve our overall minimum time. So what we do with this situation is we create a 5th job here that we're going to allocate. That's a fake job. All right. So to do that, we just create a column of zeros here to create a 5th job that has 0 time allocated to it. So we just create a column here of zeros. And what this does is it makes it a 5 by 5 array now. So previously it was 4 by 5 or 5 by 4. But now we've forced it to be a square array, so now we can apply a Hungarian algorithm. Now the thing about applying a Hungarian algorithm at this point is if we start at step 1 and looked at each row, because I've got a 0 on each row, it means that we're going to be subtracting 0. So we just skip step 1 and we go straight to step 2, which is subtracting the smallest number from each column. So the backstroke here, no matter what, it's going to cost us 55 seconds. The breaststroke, it's going to cost us 59 seconds. The butterfly, it's going to be 52 seconds. And the freestyle, it's going to be 49 seconds as the minimum time that's going to cost us. And we now create our new array. So this is going to be 1, 7, 0, where are we? 3 and 1. This is going to be 0, 8, 5, 1, and 0. The butterfly is going to be 0, 7, 6, 2, and 0. The freestyle is going to be, where are we? 40, it's actually 48. I was just looking at that going, that's not right. So it's going to cost us 48 no matter what. So that's going to be 5, 1, 3, 0, and 1. And then don't forget our column of zeros for our 5th made up task. And now from here, we repeat our next step, which is to cover up all the zeros with the minimum number of horizontal and vertical lines possible. And we can see here that we can cover all the zeros up like that and cover it all up like that. Here's our 3rd. No matter what, it's actually going to cost take 5 to get there. And because it's a 5 by 5 square array, it means that because the minimum is 5, it's going to, we're ready to allocate our jobs straight away. So we don't need to go to that next step of looking at the smallest uncovered number, we are ready for our allocation at this point. So when we look at our allocation, we can see that for person B, it's actually the last 0 here. So they're not actually going to get a job. Because person B is doing the last job, it means that we can allocate the first job to person C. Because we've allocated the last job as well, we're going to allocate the butterfly. That's the freestyle to person D, which will mean, and this is a unique situation here. It means that we've now got these 2 zeros that person A has got and 2 zeros here that person E has got that we can allocate in either order. So if we think about our allocation here, all right, so we've got our backstroke, our breaststroke, we've got our butterfly, and our freestyle. And I just say no job for the other allocation. We can see that with our backstroke, it's fairly straightforward. We're going to allocate swimmer C to our backstroke. Our breaststroke, it's a little bit more complex, so I'll come back to it. Is the freestyle that's the next one that's the simplest to allocate. So the freestyle we're going to give to swimmer D. The no job, that's pretty simple to allocate. That's going to be swimmer B. But the butterfly and the backstroke, what these double zeros like this indicate is we can allocate this either way and it's going to give us the same time. And it's not going to change anything. And if you look at the reason why that's occurring back in here, swimmer A and swimmer E both took 59 seconds for both the breaststroke and the butterfly. So because we need to allocate these 2 jobs to these 2 particular swimmers, it's not going to matter which order we allocate them. So we can either give breaststroke to swimmer A or E. And this would be the other way around. It'd be E or A. So we've got a double allocation that we can have here for these 2 particular swimmers. Now, if you wanted, you could actually rewrite the whole allocation down as 2 separate allocations. But there are times that can come up where you can allocate in a couple of different ways and still achieve the same overall time. So that's how we deal with a non-square array. The other one that we've got to think about is what happens if we want to maximize a problem rather than minimize. So what I've got here is I've got a theoretical set of scores that is going to be achieved from a debate. And you've got 3 speakers in a debate and we've got a team of 3 just to make it nice and simple here. Now, these are the scores for if person A went first, they'd get 76 points. If they went second speaker, they'd get 79. If they went third speaker, they'd get 72. We want to allocate here so we achieve the maximum overall score and not the minimum. Now, the Hungarian algorithm can't find maximums on its own. It's a minimizing algorithm. So what we have to do is we have to think about this problem a little bit differently. In that, we've got to change it to a minimizing problem. So what we do is we look for the largest number in here, okay? And we want to look at this and go, well, no matter what, our largest score that we could achieve is 81 from person B if they went to, like, second speaker, okay? Now, if I was to allocate anything else to person B, I'd be losing points, potential points. If I was to put them in third speaker, I'm losing a potential 2 points from person B. And that's the way we want to think about this, is we want to minimize the amount that we lose. If you think about the test scores and things like that, some people want to maximize the points that they gain in a test. The way to maximize the points that you gain in a test is to minimize the points that you lose. That kind of makes sense to me. So what we're going to do here is we're going to look for the largest number. In this case, it's 81. And we're going to subtract everything in the whole array from that 81 as our first step. So it's going to be 81 subtract 76, which will be 5. It'll be 81 subtract 79, which will be 2. 81 subtract 72, which will be 9. 81 subtract 77, which is 4. So 0, 2, and then 81. So that'll be 6, 7, and what are we? 81. So that's 3. And now what I've done is I've changed it to a minimizing array. Okay, so we're minimizing the points that we're going to lose here, or potentially lose through our allocation. And we now start the Hungarian algorithm because it's a minimizing problem. So we're going to subtract 2 here, subtract 3 here, which changes it to 3, 0, 7, 4, 0, 2, 3, 4, 0. We repeat this, it'll be a -3 here. So 0, 1, 0, 0, 0, 4, 7, 2, 0. We check, can we get it in any less than 3? I can't see any way that we can get it in less than 3, so we're actually ready for allocation. So how would we allocate? Well, we'd definitely go with person B onto that job. If person B is doing that job, means person A has got to do this job and person C should do this job. So we've got our allocation where speaker 1 should be person A, speaker 2 should be person B, speaker 3 should be person C. So the important steps with a maximizing is we've got to change it to a minimizing problem first. How we do that is we look for the largest number in our array and we subtract every other number from the largest number of our array. And that in essence summarizes the Hungarian algorithm. All right, so the Hungarian algorithm, I've just got on display here. The first step is we're trying to subtract the minimum number from each row. The second step, we subtract the minimum number from each column. Then we've got to cover the zeros with the minimum number of horizontal and vertical lines. And we can sometimes repeat this multiple times if we need to go through step 4. But if the minimum number is the same as the square of the array, then we go to our allocation step of step 5.